I'm Russ, and I'm part of the CactusCon registration team. It's my pleasure to introduce our next speaker today, Hypoxic owner and operator Mark Kirschenbaum. Mark's talk today is entitled Extracting a Bootloader's AES Key via a Power Analysis SideChannel Attack. At the end of the talk, there'll be a live Q&A with Mark. All you need to do to join in is have your questions ready.
Well, all right. Welcome to my talk on power analysis side-channel attacks. My name is Mark Kirschenbaum. A lot of people call me Trunk in the industry, so feel free to use that. We're going to talk a little bit about how I was able to break into the security enclave on a GoPro Hero 5 and extract its bootloader's keys. So I hope you enjoy this talk. A little bit about my background. I own and operate a company called Hypoxic. And we make camera equipment basically for extreme sports. So let's say I'm jumping out of an airplane and I want to capture an image of my girlfriend who's in the bottom right hand corner here. While I'm flying, I'm using my hands. I have to look at her. I'm using my face, and so I can't be holding a camera while I'm doing that. So we make a bunch of the accessories that mount on our helmets and enable us to capture these images or capture the video and make sure that we do it reliably. So in order to do that, over the years, I've had to reverse engineer a bunch of cameras, a bunch of embedded systems to make them work the way I want them to. I think like all of us, I really love to take things apart. And maybe in the past 10 years, I've actually learned how to put them back together. So full disclosure, I used to work for a microcontroller company. I no longer work for them, and that was some like 11 years ago. But just in case people put two together. This talk has nothing to do about them. I look forward to answering the question why I'm doing a side channel power analysis attack, why I chose to go about it this way. A little bit of the power analysis behind a side channel attack. And then obviously how to implement this in the real world, because that's where you really take the pen to the paper. I'll give you some advice on implementing this in your own target. And hopefully at the end of the day, answer any questions you have on the Discord server. Okay, side channel attacks are really, really neat. I find them they're the culmination of like everything you've ever learned in school. It bridges statistics, analog electronics, digital electronics, with cryptography, and it's pretty complex because not many of us are good at all those tasks or aspects. And so it's a really kind of a neat concept to learn and to work through yourself. Today, my goal is to pretty much simplify all of this and give you an overview. So at the end, you could work through one yourself and learn it. I'll start off with this question. What does a inkjet printer and a GoPro have in common? As most of us know that when we go out to buy inkjet cartridges, there's some kind of technological prevention measure that is put into the actual cartridge itself that prevents a third party from making these cartridges. Likewise, GoPro has introduced with the GoPro Hero 5 one of these TPMs that prevented us from making third party accessories for the cameras. So obviously, as a little bit of a reverse engineer and hacker, I wanted to figure out how to circumvent these measures. Well, how do we circumvent this TPM? Now, the easy way is just to find the security enclave and break into it and dump the keys. And then from there, we're going to do something and we're going to profit. Well, that sounds like real easy in theory, but it's really pain in the butt to do it in the real world. Obviously, these security enclaves, the first word is security, and there's a lot of security trying to prevent people from dumping these keys. So that's our whole goal today. Our goal at the end of the day is to basically dump the security enclave's contents and hopefully reveal the keys that are used to do this TPM. We found out after taking apart the camera that it's based upon a Microchip ATSAMD21. That used to be Atmel, so I use those names interchangeably. The part is very small. It's 2.8 millimeters by 2.5 millimeters. You could actually see it on the bottom here that you could see like the die that's through the actual WL CSP encasing here. It's a BGA part that gets flipped around and gets soldered on the board, and the backside looks like that black spot there. Attack surface wise, it really had a small attack surface. It had only 2 I2C buses, and then what's called an SDQ, which is a bus one wire protocol to talk to batteries to gauge their health. It has no UART and no USB. So and let's see, like we're gonna attack this. Let's attack this as a hacker, or as a company doing some security research on it. And all the times this is the flow that many of us will go through. We'll look at the update. We'll see how it updates, and unfortunately we found out that it's encrypted, so a little bit of a failure there. Then we'll go through like the interface, see maybe there's a debug command that they left into. A lot of times engineers will leave debug commands on the earlier versions before they realize like, oh shoot, I shouldn't have done that. So it's very easy to exploit those type of things. Moving on, a lot of times nowadays we'll write fuzzers, which basically just tries a whole bunch of different combinations and see if we can't make this crash. And if we make it crash, then we know that we've hit something that we weren't supposed to hit, and kind of iterate through that and try to find a method of extracting the firmware out of these devices. Continuing on, when that failed, we learn how the updates occurred. Okay, it's encrypted. How is it encrypted? There's ways of looking through that and seeing what kind of encryption it's using, and perhaps working through some development notes or app notes that companies push out, and figure out maybe they use the default password type of thing and try to decrypt it all that way. And of course that didn't work for our solution here. And then we go even further. We take apart the board, and we'll see if like the software debug port is unlocked. They didn't set a code protect key or bit or whatever they call it, the particular part calls it, or maybe there's a debug UART that was left unlocked, or maybe there's some kind of JTAG exploit that is left vulnerable. And then finally, and similarly, we would research some vulnerabilities that the host IC has, or the host microcontroller has, and there's a plethora of these out there where companies have messed up their code protection schemes, and we're easily able to defeat those. So that's kind of the where I was at, and then more or less was like, what, this is taking too long. I don't really need to do this, and I put it back, and nonetheless I failed it. And so I put this off to the side, and then COVID hit, and I was home a lot more than I expected to be, like a lot of us. And I was like, man, I saw this board on the side of my desk that's been collecting dust. I'm like, I've always wanted to be able to extract these keys. Let's learn something with all this extra time, and let's learn how to implement SideChannel attacks. Now, there's a lot of SideChannel attacks out there. There's timing attacks, which I think a lot of people are familiar with. There's voltage glitching attacks, which is basically, hitting the part on the head by bringing the voltage level down really quick in a little spike, and basically the part just skips a beat. That didn't work on the ATSAMD21. So then we had, we could do a electromagnetic fault injection, which is basically just bringing a giant EMP pulse, you can think of, and that makes the parts, skip a beat also. The only problem about that is it's fairly expensive. The tools cost about $3,800 to do electromagnetic fault injections, or EMFI side-channel attacks. So that was like off the table. But what was on the table was a power analysis attack, and that's what we ended up doing, and was able to figure out the keys by this particular attack. What is a power analysis side-channel attack? Basically, all it is we're going to be extracting the key by monitoring the power we're using during decryption. It seems pretty far-fetched, but in actuality, it works. A lot of people immediately are like, there's so much stuff going on in these microcontrollers at once, and there's no way that we're going to be able to extract at a certain time the power used and know what the key is from that. And, it's fiction. There's no way. But honestly, I've done this myself, and it does work. And I'll show you how this works. in order to show you that, the flow that I'm going to be following is I want to give you a little bit about AES, and more specifically what parts of it we need to know for a side channel attack. I'll explain Hamming weight, give you a little bit about the circuit analysis that we're going to need to know to implement this, and how the part works on the inside. The microcontrollers actually work with information. And at the end, I will give you how I implemented this attack in the real world. Here's my AES refresher for you all. If we start here, we work from right. It's so easy. Like here, you got it. Okay, and we're done. No, really. This is not my refresher, but AES is quite. It's simple in concept. I think a lot of people put a little bit too much math background when they're teaching it, and I'm going to try to simplify it for you guys. Let's simplify the AES decryption method. We're going to start with some encrypted data, and then that encrypted data, we're going to be working on 16-byte blocks at a time. Okay, so on each byte, we're going to one byte at a time. We're going to add this round key, which all that is doing is we're going to take our key, and we're going to XOR that with the encrypted data. So each byte at a time, 16 bytes in this round key, and 16 bytes of data. We're going to XOR that each location with the corresponding location of encrypted data. Okay, that's going to result in an array of 16 bytes. And in that array, we're just going to shift things around in this inverse shift rounds key. We're not doing any changing to the numbers. We're just going to shift around its location in that array. From there, we're going to take the data, and we'll talk a little bit more about this, and we're going to look up the data in that array and substitute it with a different value from a lookup table. The lookup table is just 256 bytes long, and so each byte value has a corresponding result of in this what's called an inverse S-box lookup table. Again, we're going to continue this flow. We're going to add another round key to it. And then we're going to do a process called inverse mixed columns, and we're going to be doing this 9 times. On the 10th time, we're going to spit it out, and we're going to have decrypted data. So this is what it looks like for AES-128. We're going to rinse and repeat it for 10 times. The next thing we're going to talk about is the key schedule. Let's say I have a key of all zeros. Okay, it's 16 bytes key of all zeros. And we're talking about AES-128, so we're going to have 10 rounds here. Okay. In order to calculate the key schedule, we're going to do some post-processing to this key. The first round, the key is going to be itself. Okay. The second round, it's slightly different. And as we follow through all these rounds until round 10, we're going to have the corresponding what we call the round 10 key schedule. And we can see here, this is B4, EF, 5B, CB, blah, 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 blah. It doesn't matter. So that's the round 10 key schedule. Okay, so that S box, let's just really touch base with that. We found key schedule. Let's say our output of everything was, let's say B4, right? So B4 would be the C6 here. That's all this S box, inverse S box is. It's a lookup table. Super easy. Okay. So AES for SideChannel Attacks is very easy. We're going to start with we'll start with the round key. Okay, let's all just do this at a byte at a time. Byte 0, we have round key of 0, which was B4. Let's say, was it BF? Yeah, B4. Okay, and we're going to take input. Somehow in the system, we're going to put input into it. Okay, we're going to XOR that data, and then we're going to have an output of that XOR. We're going to shove that into this, use it as the index to the S box, the inverse S box, and then we're going to get some result out. A lot of people that know AES are like, hey, Trunk, you're kind of missing a step, aren't you? Yes. This little guy right here, this inverse shift rounds, for side channel attacks, we don't really care. We really don't care, and I'll show you why in a little bit, but because we're dealing with the correlation of the data, we don't really care where in time this happens. We just care that it happens. So we preclude this, or we ignore this step in AES when we're doing our side channel attack. So don't worry about that little guy there. Now that we're all AES experts, Let's dive into the power analysis part of the attack. First, let's take a look at what we're actually working on. This is the Microchip ATSAMD21, and this is basically the block diagram of the whole system. We're going to be focusing more or less on this top area here. The Cortex M0 Plus is actually a von Neumann architecture, so it's got a shared high-speed data bus. And we'll see this as the data from RAM is going to go across this high-speed data bus. The data from flash, internal flash, or they call it NVM, likewise is going to go across this bus. So there's some kind of caching in this Cortex M0. They don't really break it out here in this diagram. There's also going to be the registers like R0 through whatever. And more or less, what we are concerned is every time we read or write from this bus, obviously there's going to be some power that's necessary to do that. Now, the basis of power analysis is when we do that read or write, the power required is going to be proportional to the data we're read or writing on the bus. Pretty nifty stuff. So let's say, for instance, I'm going to be writing into the SRAM, I'm going to write like all A's. Okay, that's going to use a certain amount of power to do that. Now, if I go ahead and I write all zeros there, it's going to be using a different amount of power. Okay, likewise with reads and writes. And also similarly, when I'm reading or writing into the registers, it's going to be the same way, that it's going to take a certain amount of power. So the power analysis basis is that. It's just that the power is is needed to do load and stores is going to be proportional to the data itself. Now, when you start hearing about power analysis, you'll start hearing terms called DPA and CPA. That's just really names for the math used to extract what the original data is that's going across these buses. For instance, DPA is called differential power analysis. You can read up on that on your own if you want to. And then CPA is it's going to be extracting the secrets using correlational power analysis. And that's what we're going to continue focusing on today. In order to explain correlation power analysis, we have to introduce a concept called Hamming weight. Hamming weight is pretty easy to explain, and generally it's just by example. For instance, if we have the value DD, all we do is we bust this out into binary, and now we have 1101, 1101. Now, for Hamming weight, all we're doing is counting how many ones there are. 1, 2, 3, 4, 5, 6. So the Hamming weight of DD is 6. Likewise, if we have a hex value of 0, the Hamming weight of it is just going to be 0 because there's no 1 in this. Okay, so all we're doing now is we take out all values that a byte could be from 0 to 255 and determine the Hamming weight of it, and we'll get basically 9 layers of Hamming weights where that a number can have. So like we said earlier, during a store, the power consumed, it's going to coincide to the data itself. We use the example of AA versus 00. The power consumed at that point is going to be, for an AA, is going to be different than the 00. And if we want to, we can probe right at this particular time, right after the inverse substitution byte occurs, and we can come up with some power usage at this particular time. We're going to take that power usage and then we're going to convert it into one of 9 Hamming weight buckets. Okay, and this is going to tell us a little bit about this information. Now we have some quantifiable information about the data that came out of this substitution byte block. So what do we do with all this? Well, what we're going to do is we're going to make a lot of guesses. Check this out. Obviously, we just talked about the Hamming weight coming out of this. Okay, so we know something about the signal. We know something about the output. We also know the input. And why do we know the input? Look, the manufacturer is going to have to push an update to you. That means that you're going to be able to somehow push this update into the victim. So we're going to be in control of this input here. We don't know, and we're looking for the round 10 key, let's say byte 0. So we know the input. We can guess. This is only 256 guesses here. Okay, we could guess this value. We know the input. We go and XOR it. We look it up in the S box, inverse S box. We come with output. We convert that to Hamming weight, and then we see if that Hamming weight, with the Hamming weight we've actually got, if they correlate, if they actually work. If so, +1 for this. If not, then we ignore it. That's really neat and all, but how do we automate this? Well, in order to show you how we automate this, I first want to show you what we're working on. To the left here is basically our power trace. I'm going to grab a pointer. So this is our power trace of probably about 50 power traces. They're all stacked on top of each other. But what you can make out is you can make out the 16 inverse substitution byte blocks here. There's 16 of these little pulses all along. If we start zooming in, you'll start seeing signals like this. We'll zoom in a little bit more, and then you'll end up with a signal like so. And you'll notice how there's these like striations, I would say, of the power being used during a one of these encryption process during the output to the inverse SBox function. And the reason why I zoomed on here is because this is actually a real world example of the kind of differential that you'll get there. Now that's where the two different types of side channel power analysis goes, is how to process this change. We're working on the correlation method. So there's really a thing called a Pearson correlation coefficient, which will allow us to basically figure out what the value is by how the data correlates with each other. And luckily for us, is the software will do it for us. And at the end of the day, all we're going to be doing is we're going to be throwing this power trace into software. We're going to say what kind of leakage model we have, and it's going to help us come up with the end up keys. I've talked a lot about correlation without actually giving an explanation of what it is. Correlation is fairly simple. It's basically the relationship. It just says that an input has a relationship to the output. So if we put a number into this system, if it correlates, that means the input has some kind of relationship to its output. So if we have a correlation of 0, that means the input has no correlation to the output. It has no relationship to the output. So basically it has, that number has nothing to do with the output. As we grow in correlation all the way up to 1 or -1, today we'll just be taking the absolute value. So it's basically going to go from 0 to 1. As we grow in correlation, you can see how our blob of data, or becomes, or scatter plot here, just becomes more and more like a line. Obviously, in a real-world system, we're never going to have a pure in a real-world power side channel analysis attack, we're not going to have a pure 1 correlation. It's always going to be, there's something else that's going to happen. There's going to be a bad sample. So we're going to get a correlation of like 0.6 or something like that, which is pretty good. But what ends up happening is you'll have all the other numbers having a correlation of, let's say, 0.2. Okay, so you have one number that has a very high correlation, and all the rest of the numbers have a very low correlation. And that's going to allow us to figure out what our original key is. So the nice thing is that we have tools that are going to be able to process all of our power traces for us. So this is what it's going to look like. We're going to put our power trace into this tool. We're going to start running it, and we're going to tell it what kind of leakage model we want. And pretty much you're going to start seeing these numbers pop up. Now this happened really quick on this particular part. We're able to do very minor amount of, or a small amount of traces, and glean out eventually what this key is going to be. So you'll see here, like we have on byte 0, we have a key of EA, and with the this is the correlation coefficient here, this 0.662. It's getting nearing 1, and the next closest one is this 0.394. You'll notice that this 0.394, 0.39, these are all very similar, which means that this one is to a high degree of certainty most likely our byte 0 key. And if we go down this row, it's going to be like the same for all of them, where for a high degree of certainty, this is our key. So believe it or not here, with 150 traces, we were able to figure out the key from this leakage model, which would be EA797920C8, blah, blah, blah. And this is the key, the round 10's key. You may be asking yourself, like, how many, like, it sounds like a ton of data that I'm processing through. And it is, but luckily our computers are fast. So let's say that we're going to take a power sample or the power trace that we just saw. Each power trace, let's say, has 5,000 points in time. Now, in each point, we're going to have to make 256 guesses. And then we're going to be doing the 16 bytes in AES-128. Let's say we are doing, like that last one was only 200 samples, but let's bring it up to like 5,000 samples. So if we do the math there, we're only ending up with 102 billion basically mathematical computations we're going to have to do. In my laptop, they took like no time at all, like less than 20 minutes, I think, for cracking the GoPro once I figured out what, the process and did all the stuff going out. And that's definitely a lot smaller than this to the 128th. So yeah, we found round 10's keys. This is awesome. And like I said 2 seconds ago, it's invertible. So we found round 10's keys. We're going to invert that to round 0's keys. From there, we're going to take the update and we're going to decrypt that. From there, I'm going to reverse engineer the firmware, patch it to allow myself to read out the software, read out the TPM keys, and I don't know, and hopefully profit. Yay! Wow, nice theory, bro. How are we going to implement this? And so that's what I'm going to talk about next. I'm going to talk about the tools that I used, how we input our own data into the system, how do we capture the power trace, what tools we use for that, how fast we need to capture it, and then how do we synchronize it so all these buckets are in the same spot, and then of course how do we process this information once we capture it. So if you're planning on doing any type of side channel attack, you really need to get one of these chip whisperers. The top one here is I think about $60. The bottom one's $260. And it basically comes with this whole ecosystem on how to learn side channel attacks and how to perform them on your own. This is the platform, the one on the bottom, the Chip Whisperer Lite, is the platform I use to carry out this attack on the GoPro. It's basically 105 million samples per second oscilloscope, has triggers, has a clock generator you could throw in as the input clock into your target, and a serial port, as well as a way of doing some voltage glitching attacks. It's an amazing ecosystem, and also it has all these tutorials on various attacks. Colin O'Finn, I think he did his PhD using this tool and then ended up selling it, and now he does all these training things. So if you're interested in getting trained up on this, he has a bunch of courses and stuff like that, and I highly recommend it. I'm not sponsored by them, but they did send me a care package after my talk because I think they were a little bit taken back by the little board that I made by the target, so he ended up sending me one of these UFO boards, which I'm definitely very appreciative of. So that, again, this is the tool that I'm going to be using for all this and the ecosystem that I'm going to be using to run this exploit. Knowing the ICE system. Since we're going to be doing a power analysis side channel attack, we now need to figure out how to push data into the part so it will decrypt it or attempt to decrypt this data. So in the case of the GoPro, what I ended up doing was I ended up sniffing the I2C protocol during the update. I found that it was requiring 144 bytes per time. There was a flag at the start that basically reset the whole process, which helped me out a lot. And this was all done during the reconnaissance stage. I then found out that it would be easier to basically hack this part if I took the part out of the GoPro system itself. There was a lot of other stuff going on in that system, a lot of switch mode power supplies and stuff that would make my life a little bit harder. So I found it's easier to actually just pull that part off, make my own circuit board, and then resolder it back onto it. This allowed me to recreate the protocol and recreate, basically make a fake update process where I'm throwing at it these 144 bytes at a time, and was able to start the first decryption process, which we would end up sniffing and creating a power trace from that process. We ended up building up a converter to help us with basically a glue logic between the chip whisperer and our target. This knew the whole update process. It basically converted the 16 bytes the chip whisperer was sending us, the 16 fake bytes it was sending us to decrypt, and it put it into that whole protocol that the GoPro was wanting for an update blob. So basically, it was asking for 144 bytes. We would expand it from 16 bytes to 144 bytes, add on the headers, and send it to the GoPro, the target, the victim, to start the update process and decrypt this data. What was really nice about this is it allowed us also to put a very well-timed trigger and throw a trigger out to our chip whisperer and to our oscilloscope to capture the power trace. So if your protocol is not necessarily if your victim is not necessarily expecting serial data, making a converter like this out of Arduino or whatnot is something I would highly recommend doing. So how do we measure power? How do we create one of these power traces? Well, it's pretty easy. We look at the power that's going to the system. In this case, it's going to be 3.3 volts. And after the bulk cap or whatever capacitors they have out there, the bypass capacitors, we cut the trace and we're going to add what's called a shunt resistor to it. In this case, it's 10 ohms. And after that, we're going to add a voltage probe. This voltage probe, and I'm not going to bore you with the math, but it basically is going to allow us to measure the voltage drop across that resistor. And from there, we're going to be able to figure out the current. And current and power we're going to be using interchangeably here for this discussion. So this voltage probe here is more or less going to be directly proportional to how much power the system uses. The measurement here is going to be directly proportional to the power that the system's using. Now, if we want to do this over time, if we want for each time or each instance in T, we want to measure the power being used, all we do is we use an oscilloscope, and that will measure, at every acquisition point, and it's going to measure what that voltage drop is, and therefore measure basically the power curve of the system. Let's see what ends up happening in the real world, though. In the real world, these microcontrollers now have a lot of inputs, a lot of power inputs. They have I/O power inputs. They have ones for their analog. They have, basically power input for each subsystem. Specifically, the ATSAMD21 had a power, what's called an internal voltage regulator for their VDD core. Okay, so in order to measure how much current or power the core is using, I had to come up with a solution. And that's where what we did here is we overdrove that VDD core to like 1.5 volts, and that shut it down, effectively shut it down. And then it was sourcing the power from this external input. Now you may be asking yourself, that's way, I'm going to blow up the part. Yeah, if it's like very hot out, or you're using this in a very heated temperature, you might definitely stress the part, but we're not using it for very long at that voltage range, so it would be fine. So anyways, if I continue on, I just did the same thing here. We ended up using a little bit bigger shunt resistor, okay, and that allowed us to have a little bit higher gain of the voltage drop across it. And also, because we wanted a very clean signal, we used what's called a differential probe, which just basically does the math for you, the difference between the voltage on this side versus the voltage on this side. And that gave us a very clean signal for the power trace that we were requiring to run this exploit. Okay, so now we have the power trace, but one of the things we got to figure out is how fast do we have to capture this power trace? How fast do we have to basically measure the current? We're going to be measuring the current at a certain beat, and we need to figure out what that beat's going to be. The chip whisperer is awesome, and one of the things it does is it generally outputs a clock. Okay, and what you'll do is you'll feed that clock into the system, into your victim, as its input clock. And what that allows us to do is allows us to capture right at the very point that the instruction is getting operated on or getting executed. So that makes this exploit so much easier because we know exactly when that instruction is going to be operated on. We can measure the current at that point in time, and we really it makes our lives so much easier. Unfortunately for us, what our target had is what's called an internal oscillator. It had its clock inside of itself. So there's ways that you could sniff that internal clock from like the EMF radiation and recreate that clock, or you could do what we did and we just oversampled it. So we oversampled it past the 105 million samples per second bandwidth that the Chip Whisperer had. And in order to do this, we ended up using our trusty oscilloscope. And we just basically took the differential probe, dropped it right into our oscilloscope, had the Chip Whisperer go to its triggers, so trigger the oscilloscope when it was capturing, and basically bypass the whole oscilloscope portion of the Chip Whisperer. Once the data was collected in the oscilloscope, we wrote a Python script on our computer to basically suck in that power trace, and we sucked it right into like the Chip Whisperer software. So altogether now, like, man, this is, you're talking a lot of hardware, but how does this all work? So let's start with what's going on. We have the Chip Whisperer ecosystem running on our computer, and this is running through Python, and this is Juniper basic notebook that we're running. This is talking to the Chip Whisperer and sending it 16 bytes of data. This data goes over serial, and then that serial to I2C host is converting this data from 16 bytes to basically the protocol that the victim is expecting for an update. It's sending it to the victim, and at that same time, it's sending a trigger to my oscilloscope to start capturing the power trace. Okay. Once that capture is completed, it uploads it to Ethernet, and then this is my whole acquisition chain that was used to capture all these thousands and thousands of power traces in order to do power analysis side channel attack. So you can see like kind of the whole setup. Here's the Chip Whisperer, talking to the computer. Over this is basically from here it was serial to my I2C to serial host, I2C over to my victim. Okay, my victim is getting, the power is getting sniffed basically, or monitored through my differential probe. This is going to the oscilloscope, which is getting triggered from here. And the trigger line from my I2C serial host is going there. So that's the same line. So basically technicolor spaghetti at this point. Now that we're capturing all these traces, how do we synchronize the traces amongst one another? Generally, if you had an external clock, it would make it real easy to synchronize that data, and the Chip Whisperer does a good job of synchronizing that data for you. Since we have an internal clock and we're oversampling, how do we make sure that all these power traces are on top of one another? Because at the end of the day, we basically need that bucket to be in the same spot for each power trace. Well, thankfully, there's a solution. Well, the solution is math. And basically, we're going to use a filter called a sum of absolute differences. And that's going to allow us to align our traces. If we look below here, I have basically I have a bunch of power traces. And I have two little distinctive waveforms here that happens on every power trace. And what I would do is I'll end up going and running this filter, the SAD filter on it, and do a coarse alignment. And it brings it fairly close. And then I'll run it through one more time and do another fine alignment, on this rising edge. So this will allow me to get them, squared up, so that when I run it through the linkage model, that it will end up finding the keys for me. Now we need to process all these power traces. And to do this, we're using something that's included in Chip Whisperer's ecosystem. It's these Juniper notebooks that basically have a bunch of tutorials on how to implement side-channel attacks on your own. The one I used was, I think, a 256-bit bootloader decryption method that he came up with. And I just basically extracted out the pieces I need. It's all Python based, so you can write your own code. And that allowed me to basically interface to my victim, or my serial to I2C converter that I built, and allow me to send the random data and capture the traces from my oscilloscope right into this Juniper notebook. At this time, I'm basically going to be saving these traces with the data that I sent the victim. Okay, so now I have basically a bunch of numbers of what the power is at a certain time, and I have the keys that the fake encrypted data that I sent to the target. And this is something that I'll will end up processing. After I have that chunk or the blob of data for each power trace, I'm going to align all the power traces with the SAD filter, like I said in the last slide, and then I'm going to basically send it into this inverse S-box leakage model and have it process all this data. From there, we're going to be extracting the round 10's keys. If you're going to attack a target like this, like let's say the ATSAMD21 or any other target that's, you have a microcontroller that obviously you're trying to extract the keys, is to create a mockup. We know what kind of encryption algorithm they're most likely using. We know what the I2C protocol, the protocol they are using to talk to it. We'll figure out stuff like that they're using internal clocks, and we're able to basically remake the system. Okay, we know everything but the keys at this point. So I would write some code, program it on the part, and then try to adjust do power traces on it, just like attack this part, and maximize or optimize your power trace. Optimize, how many points I need to find, my voltage levels, like everything, all the inputs in the systems, like my resistor value, how fast I need to capture data, how many points I need to capture, and really learn how this target reacts. And that was invaluable for me to end up extracting the key. I spent more time, I think, on this and getting this all cleaned up and right. And then once I just popped the chip in, it was very easy to extract the actual key itself. So I highly recommend this. When we're running these attacks, there's sometimes when we can't extract a key for whatever reason, like the certain key byte won't be extractable. Well, luckily that now only becomes 256 problems I have to solve, right? That byte has only 256 possible numbers that it could be, and we just brute force that. We just pop that number into the round 10 key, work our way backwards to find the round 0 key, throw in the GoPro's update, decrypt it, and then throw it in an entropy kind of post-processor to see how the data looks. If the data has a very low entropy, we know we just decrypted it. The other thing I haven't really mentioned throughout all this is the chaining mode. And for decryption, it really doesn't matter. I mean, of course it matters, but to actually figure out the key, it doesn't really matter. If we look at the bottom right-hand corner here, we have, obviously our encrypted data. We're going to go through our block cipher with the key. And then once that comes out, the first 16 bytes, at that point, we XOR in the initialization vector. So the IV for decryption only matters for the first 16 bytes. And if, luckily we had the IV of 0, so it didn't really affect us too. It was very easy. We didn't really have to do anything. But if you have an IV of anything else, you can go ahead and do a little bit of side-channel attack there. And there's ways around that. And for most of these, let's say for the Cortex or any of these parts, a lot of times it's just an interrupt table, and we could figure that out on our own. So it's not as bad as it sounds, that initialization vector, and pretty easy to circumvent. Obviously, I could have done a lot of things better during my attack. One of the things that I didn't really care for was how small I made the target board. The victim board is very small, like big. I should have used one of the new AES UFO boards, or at least made it bigger. I get so used to making everything so small. I use the smallest resistor values. I have 0402s, and that really made it a lot harder to run this attack. So definitely make it bigger. EMFI would have done this a lot faster, and that's kind of like the way of the future. I think a lot of people are not doing power analysis side channel attacks as much anymore because these EMFIs or even laser attacks are really powerful and really quick. Again, start small, make your mock-up, learn all the samples on the new AE, Juniper, ChipWhisper, ecosystem, like run through all that stuff so you really understand it. And like I said, create your own mock-up there. And obviously, like any of the stuff, you just need to do it. You just need to run with it and try it out yourself and see how it works. At the end of the day, just make sure that you're not going down a rabbit hole. That's pretty much what this whole thing was. I mean, I'm grateful that I spent the time to learn how to do a side channel attack on a target such like this. But at the end of the day, I really didn't need to do it. I mean, I spent a lot of time figuring out how to do it, but make sure you're not going down a rabbit hole with this kind of stuff. Make sure that there's not easier ways of doing it or ways to circumvent that, because it's very easy to go down that with side channel attacks. Where to go to next? If you're really interested in doing your own side channel attack, I would highly recommend these videos or articles. I have a really good article on my website under my blogs on this whole attack. It goes a little bit more into detail. If you're a little confused about AES still and want to learn a little bit more, this computer file video did a great job of explaining it. And of course, for side channel attacks, I would definitely just check out New AE. They have some really good resources on learning how to do side channel attacks. And this video in particular was instrumental in teaching me how side channel attacks work and what's the premise behind it. So highly recommend that. Well, thank you for sitting through my talk. I hope you learned a little bit. If you want to get in contact with me, feel free to follow me on Twitter. It's at GetHypoxic. On Instagram, I have a bunch of my photographs and some video. That's at GetHypoxic also. And likewise, if you want to read some of my blogs, feel free to check out gethypoxic.com, where I have all my technical blogs and whatnots. Well, thank you again. And if you're listening to this live, I will be answering questions on Discord in a little bit. Bye now.